This video goes over using the rate of change formulas, the instantaneous rate of change and the average rate of change, in order to solve word problems. So in this question it says the movement of a certain glacier can be given by d at t is equal to 0.01 t squared plus 0.5 t, where d is the distance in meters that a stake on the glacier has moved relative to a fixed position t days after measurements began. Find the rate at which the glacier is moving after 20 days. So here we're going to find our instantaneous rate of change at 20 days. So we're going to use our IROC formula, or instantaneous rate of change. This is also the slope of our tangent. We're going to find the limit as t, the variable from our function, approaches a. And we're going to use our original function, d at t, take away d evaluated at a, all over t minus a, where our a value is 20. And so what we're going to do next, this is our limit formula from our tangent note. And here we're really just doing y2 minus y1 over x2 minus x1, except our notation is fancier because we're working with functions instead of lines. So on our next line, let's sub in what we know. We know that a is 20. Our distance function is 0.01 t squared plus 0.5 t. Our next point is we're taking away our function evaluated at a, so at 20. So let's take a minute, we'll do that off to the side. So we're going to substitute in 20, which means that we put in 20 wherever we see that t in the function. 20 times 0.5. And when I evaluate this, I get that d at 20 is equal to 14. So then the second piece on the top of my formula, I'm going to take away 14. On the bottom, I've got t minus 20 because that is t minus a. So if you remember from our tangent practice, the only thing that we know how to do is factor and cancel out the bottom term. So I'm going to factor out my a value so that I get a simple trinomial. And this gives me 50t minus 1400. I know that as long as I've done my algebra correctly, one of the factors of the top should be t minus 20. So that lets me fill in the other one because I know the final two terms have to multiply to minus 1400. That is going to let me cancel out t minus 20. And then I'm sitting with the limit as t goes to 20 of 0.01 times t plus 70. To evaluate my limit, I'm going to substitute in 20 for t and drop my limit notation. So I get 0.01 times 90, which gives me 0.9. This is a word problem, and so I do have units. It's changing at a rate of 9 meters per day at 20 days. So in the next example here, we're looking at the profit in dollars of manufacturer selling digital phones is given by this function here, where x is the number of phones sold. Here we're looking for the average rate of change, so not the limit of profit from 100 phones to 150 phones sold. So here we're looking for our average rate of change, which is our y2 value minus the y1 value all over y2 minus y1. Now I got those values from here. So I've got x1 and x2. Those are my x values that I'm comparing. On top, I'm looking for the difference between my y values. My y in this case is p at x, and so I'm going to evaluate p at x1 and p at x2, and I'm going to find the difference between those two values. So when I evaluate p at 150, I'm taking 150 and I'm substituting it in wherever I see an x in that profit function. When I evaluate that, I'm going to get 25,875. And then when I do the same thing over here for 100, that means that I'm taking x is equal to 100 and I'm substituting in to my given function, and I'm evaluating the y value at the given x value. This is 16,500. And so when I put those values in, what I'm going to find is I've got the difference between my y values divided by the difference between my x values, which is going to give me 9,375 divided by 50, which gives me an average rate of change of $187.50 per phone. It is important to have the units because we are dealing with a word problem. The second part of the question is same function, but now we're looking for the instantaneous rate of change after 3,000 phones are sold. So this is going to tell me my A value, 1,000. Instantaneous rate of change should make you think of the limit. So when we're doing our instantaneous rate of change, we are finding the limit as x goes to 3,000, and I'm using the y value at x, take away the y value at a, all over x minus a, just plugging into my function. So now if I go to evaluate p at x, that is just the function that I'm given. Not 150, should be x. So we've got p at x, x squared plus 200x minus 3,000. And then my second value, I'm evaluating at 3,000. So anywhere I see an x, I'm going to put a 3,000. Plus 200 times 3,000 minus 3,000. And this is going to give me this should be 147,000 here. Okay. I also think I've got one too many zeros up here. Doesn't change the value, just too many zeros that I wrote down. Okay, back to finding the instantaneous rate of change. So now I'm going to substitute in those values that I know. I'm going to keep writing the limit down because I haven't evaluated it yet. P at x is just my function, which is kind of long in this case. And then I'm going to take away 147,000 because that is my y value at 3,000. And then on the bottom, I've got x minus 3,000. So now the only thing that I know how to do is factor and cancel. So I'm going to follow the same approach here that I did above. I'm going to factor out minus 0.05 so that I get a simple trinomial. This is going to leave me with x squared minus 4,000x plus 3 million, I think, here, all over x minus 3,000. So now I need to factor this simple trinomial. And I know that because the only strategy that I know is to be able to cancel with the bottom, I know that one of the factors is going to be x minus 3,000. That allows me to fill in the other factor. Then I can cancel those. Now I'm going to be able to evaluate the limit. So I've got the limit as x goes to 3,000 of 0.05 times x minus 1,000. When I substitute that in, I'm going to get minus 0.05 times 3,000 minus 1,000, which is cool. This is a negative rate of change. So you're actually losing $100 per phone when you get all the way up to manufacturing 3,000 phones. And those are some examples of how to use the average rate of change formula and the instantaneous rate of change formula in the context of a word problem.